Welcome everybody to our presentation for the 2015 MAA PIC math competition. My name is Zach Stuck.
I'm Daniel King.
And we're the two representatives from the University of Pittsburgh Courier Forecasting team. So to get started, so the courier company called FedUps came to us with a problem. This company transports packages all throughout the United States. And they had a problem. They don't have a very good method to forecast like how many volumes of packages and different things are going to have in different cities, especially during peak shipping purposes, or peak shipping times, or like around Christmas time. So what they want us to do is help them better predict the volumes they're going to have at different airports, and then also where those volumes of packages are going to go throughout the country.
So to kind of put this problem in terms of a visual, we're trying to determine how much will be exiting a given location. So for example, we want to know how much will be leaving Memphis for the next 12 months. And we also want to know where it will be distributed among the remaining airports that we're considering. We're considering 28 in our model. So the data, FedUps gave us 153 airports worth of data. The model was built for 28, however, it could be extended to deal with all 153. The actual data we used was FedEx data that we took from the Department of Transportation website. So this is an overview of our solution. So we broke the problem into two separate steps. So the first step was determining the volume being forecasted leaving a given airport for the next 12 months, and then where that volume would be distributed. So the first step for the user would be to input the airport data from the past few years in an Excel macro we created. The next step, they would call the forecasting function within that macro, and then the macro would run an SREMA algorithm through a MATLAB executable, and it would output the forecasted monthly departing volumes, and we're at a 98% accuracy with that. The second step would be the volume distribution. So within the same macro, it will call the distribution function, which is matrices of past month probabilities, and this will tell us the output of the next 12 months, and we're at a 90% accuracy window in the distribution.
So after some initial analysis, we realized that the data showed some linear trends, and after running some linear regressions on the data, we realized that we could accurately forecast volumes for months in advance at about 85% accuracy. So after that, we looked into some other methods and kind of came across the ARIMA model, and we kind of delved into that because of its ability to forecast time series pretty well. So what ARIMA stands for is Autoregressive Integrated Moving Average. So with ARIMA models, there's three parameters, P, D, and Q. P is the number of autoregressive terms. So basically what that is the term uses past terms to help estimate future ones by the weighted sums of those past terms. So to predict month 6, it uses months 3, 4, and 5, and it puts more weight on 5 than 3. The D parameter is the number of non-seasonal differences needed for the data to be stationary. So what this does is it differences the data and allows for normalizing the data and for a relative comparison. And the last parameter is Q, which is the number of lagged forecasted errors, and this is the order of moving averages power. So this is the general forecasting equation, Y being the forecasted term, U being a constant coefficient of the mean, phi being the autoregressive operator, theta being the moving average operator, so both of those are correlated to P and Q, and Y, the Y values are the difference data. So now what I'm going to do is just give you some examples of what an ARIMA model may look like. So this is an example. It's a first order autoregressive model. This is when the series is stationary and autocorrelated. So here's the general equation, Y again being the forecasted term, this being the mean, the mu term being the mean constant, and then the phi term being that autoregressive term that takes into comparison the past sum values. Another example is a random walk model. So this is when the data is not stationary. So you take this difference of the data, which is this Y term, add it to that mean constant coefficient, and you get the predicted value. And our last example is the difference first order autoregressive model. And this is kind of combining both of those. So again, Y is the difference data, and phi is that autoregressive term that takes the past sum values and helps predict the YT value. So that's kind of like the base model of how we forecasted this problem. But to better forecast, we used what's called SREMA, which is the seasonal ARIMA. And the only difference is it has 3 more parameters, capital P, capital D, and capital Q. They all mean the same thing except for they're seasonal. So instead of using the forecasting just on previous data, so to predict month 12, you use month 1 through 11's data. You use month 1 through 11's data, while also using previous years of month 12 to predict the future month 12. So for our model, we use R to write a code and it looped through all of these different SREMA models here. Like I said, I showed you guys some examples. These are a little more technical. So it loops through every single one of these AREMA models. And after it ran each one of these models on the data, each one spit out a BIC value. What BIC means is the Bayesian information criteria. So when you're fitting a model to data, you're likely to add more parameters to help better fit the model, and this may cause a problem in overfitting. What the BIC does is it resolves this problem by adding a penalty term. So each one of those SREMA models that we test with the R code spits out a BIC value, and then the lowest one is the best model. So our model goes through every SREMA model, it goes through the BIC values, and then picks the best one. And the BIC value is relative, not absolute, so it's the lowest relative to the other models, not closest to 0. So just as an overview of what we did, so the user inputs the monthly raw poundage data that we accumulated from online. You select whatever airport you wish to analyze. The model picks the best SREMA model with that BIC value, and then it forecasts the monthly volumes for the following 12 months. So what we did to kind of test the accuracy of our models, we used the data from 2010 to 2013 to predict 2014, which we already had, and compare it, and we found that we were about 98.2% accurate.
So the next step was extending this to volume distribution. So we thought to use probabilities initially. So for a specific airport, we would first sum all the packages skipped within month 1 of that airport from 2010 to 2013 or 2010 to 2014. Then we would determine the probability of specific airport pairing, so Memphis to LAX, for example. And we would do that by summing all that was shipped within that pairing over the past 4 years. And then we would divide that by the total sum, and we put that into a 1-by-n matrix. So the next slide is an example of this. So if we wanted to determine the probability of going from LAX to Memphis in 2014 month 1, we would take the total sum, which is roughly 106 million, shipped from LAX in those 4 years, divided by the 61 million shipped within that airport pairing over the past 4 years, and it would give us the probability of packages, which is around 0.57, so 57% of packages leaving LAX should be going towards Memphis. So then we would repeat this for every airport pairing considering our model. So this example considers 7, and we would make a probability matrix P. So we would deal with the distribution. So from SREMA, we would have an X value, which is a scalar saying this is how much will be coming into the LAX airport, for example. And we would multiply it by the probability matrix we just created, the 1-by-n matrix, and then this would give us the desired forecast of month 1, 2014. So for example, if we wanted to determine 2014 being shipped out of LAX, SREMA gave us around 31 million being shipped out of LAX in that year. So we would multiply it by the probability matrix that we just determined, and that would give us the forecasted distribution values. The error for this is very small. It's roughly 7.6% on average. So we're around a 92% accuracy in our monthly predictions for 12 months in 2014.
So for the deliverable, obviously people in the industry don't really know how to use these algorithms and these models that we're using. So we actually rewrote the code in MATLAB and then used that to have an executable in an Excel macro. It takes about 4 minutes to run. So here's some screenshots of what it looked like. So here on the left is you hit the command button and this pop-up window comes up and you enter the file data, like the data file that you have in the syntax given, hit OK, and then this pop-up window comes up and you enter whatever airport code you'd like to analyze. And after that, it spits out a monthly total of departing that airport. So month 1 obviously for January, 12 for December. These are the monthly totals departing that airport. And one Excel worksheet, and then in other Excel worksheets, it gives you the monthly distributions to all the different airports. So obviously you can see these are all the different cities, and obviously you can see down here month 6, 7, 8, so there's different months.
So from this project, we learned a lot of different skills and trying multiple attempts at a solution. Specifically, we looked at programming in R, Python, Visual Basic, and MATLAB. We initially wrote the program in R, and then we had to transfer it to MATLAB to make an Excel executable.
And we used a lot of different theories. Markov chains we discussed, but we used mainly AREMA and SREMA models. And we also had to do a little bit of contract negotiation with this FedEx company. But that's all we have, so thank you all for coming, and